And now, on to the presentation, the hidden cost of your isolated system design. It's my great pleasure to introduce today's presenter, David Carr, Applications Engineering Manager, Analog Devices Incorporated. David Carr is the Applications Engineering Manager in the Interface and Isolation Group at Analog Devices Incorporated. He has spent much of his career involved in the definition, development, marketing, and application support of high-speed analog and mixed signal products. He received his BSEE and MSEE degrees from Binghamton University. It's with great pleasure I now turn this special session over to David to begin. David, take it away.
Well, thanks, Chris. The agenda we have for you today is on the screen here. We're going to go through a brief introduction of isolated systems and why they're used. We'll talk about some market trends and some isolation trends that are driving system design requirements. And then we'll get into a few hidden costs, some things that can impact the risk and time to market on an isolated system design. We'll talk about some available solutions and some of the shortcomings that those have. And then we're going to get into a new solution for isolated power delivery. So isolated systems are used in many applications, and the most common reason for adding isolation to a system design is the existence of hazardous voltages. In many systems, there are voltages that are hundreds of volts and even thousands of volts, and there are requirements that are codified in standards to protect users, protect people, and also protect equipment from those high voltages. And then there can also be temporary overvoltage conditions or faults that can lead to hazardous conditions as well. And there are many local and global regulations that mandate safety in these situations. In some cases, the isolation is added for performance benefits. And in that case, there's no real compliance to a standard that's required. And these situations can be the elimination of ground loops, adding fault tolerance to a system, and to segregate noise so that a sensitive part of the circuit isn't interfered with by other noisy parts of the circuit. The main objectives at a very high level for the isolated system is to obviously maintain that isolation, maintain the safety, and that's done by limiting the current flow to either zero or a very, very small amount. And then at the same time, providing very good performance, so withstanding those voltage ratings, dissipating a small amount of power, having very good timing characteristics, and very high reliability. There are some trends in the market that are impacting isolated system designs. In general, many people are driving towards smaller and lighter systems for obvious economic and efficiency benefits. Also, there are trends toward higher voltages in many systems. So one example would be in the battery stack of a electric vehicle or hybrid EV. Today, it's very common to find 400-volt DC batteries in those vehicles, and by the year 2024, it's estimated that 40% of vehicle output will be either electric vehicles or hybrid electric vehicles. So there's definitely a very big trend in that direction in the automotive space. And in the industrial area, there's a lot of talk about Industry 4.0, and this is really just an explosion of sensing and connectivity in factory automation environments. And what this is doing is pushing much higher speed communication to the edge of the system, and just producing many more requirements in that area. Because you're talking about factories, there are always very high reliability and availability requirements. So the performance needs are there, and they're getting more stringent. And then in general, we're just seeing a lot of convergence of technology. You see different types of technology from consumer merging into industrial, and along with that convergence comes increased density, and also many compatibility problems can arise. Now, there are a few trends in the isolation side of things that are also changing the way that people are doing these designs. One example would be in the convergence of various electromagnetic compatibility specs, or EMC specs. The example we're showing here is the convergence of radiated emissions requirements. In the past, there were separate standards that governed information technology equipment and industrial equipment. These were CISPR 22 for IT equipment and CISPR 11 for industrial, scientific, and medical equipment. Today we have a single standard called CISPR 32, and that combines the requirements for both of those standards. And you'll see on the following slide that in some cases that makes the design a bit more difficult. Another example would be in the medical electronics space. The standard involved here is called IEC 60601, and the latest edition 4, has some fairly substantial changes. In the past, some particular environments such as emergency medical service, like an ambulance, or in the home, or an aircraft, those were considered special cases and they had special requirements. The more common, normal environment was in a hospital or a clinic. Now those are all considered normal. So all of those special requirements that apply to home, aircraft, etc., are all now bundled together with the existing hospital requirements, and again becomes more challenging to meet those requirements. So here's an example that shows how the convergence of the radiated emissions specifications have made the designer's job a bit more difficult. The plot here shows the mask requirements for the different standards as they existed prior to the CISPR 32 spec being enacted. So the top light blue line shows the maximum emission amplitude versus frequency for CISPR 11 Class A, Group 2 Class A. And these are the highest limits, so they're the easiest to meet. The next lines down, the blue and the green lines, show the CISPR 22, also referred to as EN 55022. And these are at a lower level, therefore the emissions have to be of a lower magnitude, and they're more difficult to meet. Now, once you've merged these together, the new limits for CISPR 32 are the same as those for 22. So if you were already designing a system to CISPR 22 for IT, it's not a big change for you. In fact, it's basically transparent. But if you were working on an industrial system that had these easier limits, now suddenly you have limits that are 10 to 20 dB more difficult, and so your design challenges just got ratcheted up quite a bit by this convergence of the specifications. Let's start talking a little bit about some of the hidden costs. So the first one would be in terms of safety certification. I mentioned that there are a number of standards that exist that govern the areas where safety is mandated. I'm showing here on the screen a number of different logos of different standards bodies, and these are international or regional bodies. They're listed on the right side there. Some of them, like the IEC, predominantly are writing and enforcing system-level certifications. Others, such as UL, will write both system-level and component-level certifications. A lot of the regional bodies exist because there are different requirements in different parts of the world, and so even when there's an international standard that comes from the IEC, for example, the local agency may apply their own requirements, such as local line voltage requirements or different environmental differences, because of the local conditions that exist there. So even though there might be a worldwide standard, it'll change to some degree at different locations. And having a large number of different types of standards, having them be modified in different parts of the world, adds quite a bit of complexity depending on where the end product is going to be sold. So that's one potential hidden cost that you need to be concerned with. So another hidden cost would be the increasing density that we're seeing in a lot of system designs. And In some cases, such as in factory automation, you might see a case where there's an existing footprint for a particular controller, for example. But because there are so many more sensors and actuators in the system, they need to have more electronics in that same space, and so that obviously drives density. As a system designer, now you have to put a lot more functionality into an existing space, and it forces trade-offs in terms of functionality. It may impact your schedule, and this is really due to the limited availability of solutions to meet those requirements. We're seeing a very similar trend in instrumentation. In some cases, the physical box size is shrinking while the electronics content is doubling or even quadrupling in some cases. So there's a really massive push towards density in some of these areas. Okay, a third hidden cost would be reducing radiated emissions. There are a number of classic EMC mitigation techniques that can be used to help improve performance in this area. You can add ferrites and capacitors onto the circuit board. There are beads that can be added, and you can even add metal shields and things like that. Obviously, adding these parts adds to the component count, the size of the system. It can take longer to design to make sure you've chosen the correct parts and tested their efficiency and effectiveness. And because the EMC testing is carried out in specialized chambers, it can be time-consuming to test the circuit, determine whether or not it meets the requirements, and go back and potentially modify the design. The drive towards smaller and more dense circuit boards also means that there is less space to employ these mitigation techniques. And the final hidden cost is just the complexity of adding isolation to the system. It is a specialized expertise, and it can add cost and time to your project. An additional factor that can increase the complexity is the need to transfer power and data across the isolation barrier, and the need to have multiple power sources that are brought across that barrier as well. So all of those things can add cost and time to the project and risk. So we need some way of managing, these risk and cost elements that we've been talking about here. In a traditional design, you're trading off, one thing for another. You might want to keep the application very small and meet your EMC targets, but that might hit your deadline. Or you might try and really make sure you get things done on time and hit the EMC target, but now the application is bigger than you wanted. So you really want solutions that will help you meet all of these requirements simultaneously. When you talk about EMC mitigation, the graph on the right here talks a little bit about the need to look at EMC mitigation early in the design cycle. The curves here show versus time the number or the availability of techniques in blue and the cost of implementing those techniques in red. And you can see that what it's showing is that early in the design there are many options for mitigating EMC, and generally the cost is low. And most of that is because you're not delaying the project. As you move further through time and you get to the point where the system is ready for production, if you need to do an EMC change, then the cost becomes very high because you have to now retest and recertify everything. And then the availability of options is much lower. You're really constrained now because you have a completed system design that you probably don't want to change very much for multiple reasons. So we talked a little bit earlier about the complexity around transferring power across galvanic isolation barrier. So one very traditional way of doing this would be with a discrete flyback converter. These are very common. They've been used for a long time. Generally speaking, they have a relatively low bill of material cost, but there are some drawbacks. Obviously, looking at the schematic on the right here, it's a very discrete design, so there's a certain amount of engineering effort to select the components, to test it, to produce a test plan, and you also have to worry about whether or not the components selected here are going to meet the safety requirements. Using optocouplers in the circuit here causes performance problems over time because the optocoupler characteristics change versus time over the lifetime of usage. So while it looks like a good choice from just a raw bill of materials point of view, it definitely adds a lot more engineering time. It adds a lot more risk. You could have problems in your EMC certification and have to go back to the drawing board, and as we saw in the previous slide, that can get quite expensive. So overall, looking at a very discrete implementation like this is not necessarily the best answer. So we have a new solution on the market. This is the ADUM 5020 and 5028. These are low-emission, isopower integrated, isolated DC-to-DC converters. And in a very small, compact set of packages, they provide up to a half watt of isolated output power. The ADUM 5028 is in the smallest package available for this type of component, and both of the products simplify EMC certification because they will fully meet the CISPR 22 emissions targets to the Class B limits on a very simple two-layer printed circuit board. And they also have a number of safety certifications in advance of your design, so that it gives you a lot more confidence to have the system meet the EMC tests once you go to production. So as I mentioned, these parts will meet the Class B limits on a very simple two-layer circuit board. And just to illustrate this, on the left we're showing a four-layer design. You can see the red top layer. The green is the second layer, and that area is an overlap capacitor, the top plate of an overlap capacitor, what's called a stitching capacitor, and it's made with the inner two layers of this four-layer board. And the stitching capacitor, it was used traditionally to help reduce radiated emissions performance, and it's fairly effective. However, you can see that it does take up a fairly large area compared to the overall size of the component itself. Now, the ability to pass the same Class B limits on a two-layer board means that now the overlap capacitor, that stitching capacitor, is not required, and the area required here reduces by about 70%, depending on the implementation. Now you're really just limited by the density of the actual chip itself and the support circuitry around it, and not driven by the size of that capacitor. So the ADUM 5020 is available in a 16-lead wide-body package, and it provides up to 100 milliamp maximum output load. The ADUM 5028 is in a much smaller 8-lead wide-body package and provides up to 60 milliamps. And we've tested each of these components in a certified 10-meter chamber. I'll show you the results here right now. So this shows the very simple two-layer PCB that we use for all of these tests. There's no overlap capacitance at all. There's simply the 8-millimeter gap between the left and right sides of the circuit. The only thing that's added to help meet the EMC requirements are two very inexpensive ferrites. You can see in the upper right-hand corner we've blown up that part of the layout, and the components E2 and E3 are the ferrites that I mentioned. They are very inexpensive. It is important to pick ferrites with the proper characteristics. The way that they work is by blocking the radiated energy at specific frequencies that the part operates at. And you can see the impedance curves for the ferrite that was chosen, and these were chosen specifically to have the characteristics we want at these peak frequencies. This plot on the left shows the ADUM 5028 at full load with 50 milliamps, nearly full load, and the plot is showing the Class A limit in orange, Class B in blue, and the actual measured quasi-peak spectrum below those. And the table demonstrates the margin that we have. It's better than 9 dB below the the specification limit. So it's got quite a bit of margin to the requirements. Plot is the same condition, only with the 5020, also with a 50 milliamp load, and just demonstrating that we still have very good margin. So there's very little performance difference between the two packages in terms of the radiated emissions. The only real difference is the higher output capability of the ADUM 5020. And here is the ADUM 5020 at its full load of 100 milliamps, and again, showing good margin to the Class B limits of about 5 dB microvolts. So in summary, this family of products provides a nice compact solution that meets the CISPR 22 Class B requirements. Products reduce the complexity of your design and reduce area since there is no stitching capacitance needed. Your overall material costs go down by up to 30% because you're switching from a 4-layer to a 2-layer printed circuit board. The application size can be reduced by up to 40% by eliminating that stitching capacitance. And overall time to market can be improved since the part is fully certified and pre-tested to EMC requirements and can help reduce the design time and minimize any design iterations that might have been required in the past. So in conclusion, we've talked a bit about some of the market trends and some of the isolation trends that are making isolated system design more difficult and more risky. We've gone through some of the hidden costs that are in there, things like EMC specifications that are merging, some of the global and component level safety certification requirements that change from one place to another. And then we introduced a new certified and documented family of isolated DC-DC converters with EMC test performance that has been demonstrated. These parts can help really reduce the design complexity, help you ensure EMC compliance, and overall reduce the risk in the system design. That's all I have. Back to you, Chris.
All right, thank you, David. We're now going to move on to the question and answer portion of our event. So let's get on with our first question here for David. David, what is the difference between Class A and Class B, and why is it good to have a margin?
Well, thanks, Chris. That's a good question. So within the various CISPR and EN 55022 type specifications, there are two sets of limits, as we've talked about. Class A is for equipment that's marketed for use in industrial and non-residential areas, where Class B is for equipment that's going to be used in residential environments. Class B limits are 10 dB more severe than Class A limits generally. It's good to have margin because there can be differences from one EMC test house to another. And these are affected by the quality of the test chamber and the calibration, the accuracy of that equipment. So, typically you want to have some layer of margin so that if you move from one house to another in doing your system certification, you won't end up going over the limit.
All right. Thank you, David. We're going to move on to our second question for you here. Why do isolated power supplies radiate?
Well, the reason is that we are integrating a very small transformer into the package, and this is our power transfer device. And because of its small size, it only has a few windings. It lends to the need to go to a higher switching frequency to efficiently transfer the power to the secondary side. An ideal transformer driver would be purely differential, but because of small mismatches that exist, there can be some common mode currents present that go across the barrier. And with these very high switching frequencies up to 200 megahertz, the parasitic common mode currents can capacitively couple from the primary to the secondary side through the windings of the transformer. And due to the nature of the barrier, there's no physical path for these common mode currents to return to the primary side. So the isolation barrier and the common mode currents form a dipole, and they radiate as that common mode current returns to the primary side. Now, we've done some things in the ADUM 5020 and 5028 design by improving the coil design and the coil driver circuits that help reduce the transfer of commutator currents across the barrier, and that's one of the things that helps us improve the radiated emissions performance.
All right, thank you, David. Looks like we have time for just one more question. This one asks, this family has an expanded temperature range of up to 125 C or Celsius compared to earlier generations. So what's the available output current at 125 C?
The ADUM 5020 at a 5-volt input and 5-volt output have a max output current of 100 milliamps or 500 milliwatts up to 85 degrees C. As the ambient temperature rises above 85 C, there's a thermal derating of that output current of 1.75 milliamps per degree, so that at 125, the max output current is 30 milliamps or 150 milliwatts. The ADUM 5028 has a maximum output current of 60 milliamps or 300 milliwatts up to 85 C. The thermal derating is a little bit lower at 1 milliamp per degree, so that at 125, that part is capable of producing 20 milliamps or 100 milliwatts.
All right. Well, thank you, David. That is all the time that we have for questions for today. Once again, I'd like to thank David for a great presentation and Q&A session, and I'd like to thank our audience for joining us. For more information related to today's webinar, please visit any of the resource links available in the green folder icon at the bottom of your screen. And within the next 24 hours, you'll receive a personalized follow-up email with details and a link to today's presentation on demand. Once again, if we didn't get to your question today, someone will get back to you after the program is over. And we'd like to thank you again for attending today's webinar, The Hidden Cost of Your Isolated System Design. And the individual speaker is solely responsible for his content and opinions. On behalf of our guest and Analog Devices and Arrow, I'm Chris Keach. Once again, we'd like to thank you for joining us, and we hope you have a great day.